My name is Ivan. I'm going to talk about physical AI, and physical AI that will understand the physical world. And before that, I just want to say a few words about AI in general, is that this is the most exciting things which happened in the last few years in technology. I mean, I think we all agree. And there's a lot of sort of confusion and misunderstanding what's happening. People worried about disruption. People worried that AI is going to change things so much, they will become like these dinosaurs, and you obviously don't want to be one of these dinosaurs, right? People worried that, and almost intimidated by the AI, right? They talk about like artificial general intelligence, it's almost some sort of like super smart alien coming from space and so smarter than us. What are we going to do? What are we going to do about this stuff? However, if you actually look kind of like objectively at where we are with AI and look what we have right now, what do we have right now is a chatbot. And it's sort of like having, the way I see this, it's almost like having some very nerdy friend who you can call anytime with the questions when you're solving crossword puzzle or some sort of doing homework assignment, something like that. It's not really alien yet. It's not really AGI yet. It's simple. And I think the problem there is that today's AI is fundamentally focused on understanding what is online and trained on the online data only. And most of the things which are online, we already know how to solve. Maybe I cannot solve it, but somebody else can solve it. As a humanity, most of the information online is something we already know. However, the biggest problems which we are facing right now as humans and as individuals are not on the digital world, they're in the physical world. And this is because the world is getting more and more complex. It's much more complex than 20 years ago, 30 years ago, 50 years ago. And humans have fundamentally difficulty understanding the physical world. We've been trying to understand the physical world for the whole our existence. All the scientists and engineers and economists, that's what we're trying to do. And it's just getting more and more complex. And we often don't know why things are happening and what actually is happening. So that's where we need the help from AI. That's what we think you need help from AI to understand the physical world. And so using AI I should say first that using AI and machine learning to understand the physical world definitely have been going for a while. People have been building AI solutions and trying to make sense of the physical world, and that requires to understand sensor data, because the way we perceive physical world through machines is using a variety of sensors. So to build AI for physical world is fundamentally build AI which understands the sensor data. And it's not simple. And let me go through 4 reasons why it's not simple. I'll show some examples from my previous work, why trying to build sensor system based on AI is very difficult. First of all, the number of data which world generates is absolutely huge. A single car would generate 4 terabytes of data every day, multiplied by the number of cars, you can see how much data is there. And you add any physical objects on top of that, it's just a huge amount of data. And furthermore, this data is extremely diverse. The car not just generates 4 terabytes of data, it generates 4 terabytes of highly different data, and the data coming from the radar in front of the car to the pressure sensor inside of the car is completely different. And it's really hard to access. We often talk in the company that sensor data is this dark data which is not visible. So people talk about right now, well, there's not enough data, all these models, they scrape all the data on the internet, but what you see is on the internet is like a top of the iceberg. It's the things everybody can access to. But the data with sensors is something what we call dark data, which is hard to access, but it's a huge amount of that. So we're just beginning with AI. The data is there. Second reason is that in order for AI to work in the physical world, you really have to fuse multiple kinds of data together. It's about multimodal fusion, just like humans do. We have 5 primary senses and 30% of our cortex, and the cortex is the most important part of the brain, not like gooey stuff in the middle. The 30% of the brain is dedicated to fusing this variety of sensors together to give you experience of the physical world. You don't separate vision from audio, from touch, from smell. It's one story. How can AI do the same thing? And it's difficult too because the physical world sensor data is also extremely complex and hardware dependent. every piece of hardware would produce different data. Let me give you an example, actually, from my previous work. When I was at Google, we built this project called SOLI. And SOLI was a world's smallest radar, which we co-designed with a company called Infineon, a German company, where we took this big box of current radar sensors and shrunk it down to a small chip and put it in a variety of the devices in Google products. The way the radar works, when we started working, is that it creates basically electromagnetic field, its output electromagnetic wave, and captures a reflection from the wave. That's how it works. The wave goes out, captures the reflection. And then when the person moves the fingers, the wave changes. So when we did this project, we thought we were going to get something like this, like a picture of the world. It will be easy to understand for us as humans. What we got is something like this, which is and this is all physically correct representations of radar data, and it's very hard to make sense of it. And that's the problem with all the radar data. You have to have an expert, and that stops you from building things. And then finally, is that physical data is spatial, which means that meaning of the sensor in the physical space depends on where it's located. The same data coming from the kitchen, if you have a sensor there, versus from a living room coming from there, have completely different meaning. Let me give you another example of a project we built when we were at Google. So this is the experience we did for the retail company, where the person moving physical objects create digital twin on a screen, and as you're coming closer to the screen, the display changes. So the gesture of rotating this object depends not just on the physical object itself, but how close you are to the screen. And the information changes depending where you are. Let's take a look again. So the person coming in has a T-shirt, comes in the first stage, and the first stage it shows like general information, and as the person comes closer and closer, the information changes with the same gestures and the same sense interface. This is a simple example. This is one of the biggest problems with sensors, is that you have to understand where people are and what's the context of interaction, or context of machine, or context of things. So as a result, what do we have? We have that to solve those techniques, people were building very small models for every use case. Every sensor, every task, every problem, people would build small AI models. This very fragmented, a siloed ecosystem of small, tiny models, each of them very hard to change. They don't scale because they don't learn from each other data. There is no fusion. And at the end of the day, it becomes very expensive. It's very expensive to build those models, and most companies cannot afford it. And many problems, therefore, are not getting solved. The real problems in the physical world don't get solved. Again, let me show examples from the SOLI project. When we finally shipped SOLI, we shipped on the Pixel 4 at Google. One of the use cases we're using for gestures, using a radar for gestures in front of the phone. So like whenever you have an alarm, or whenever you want to control the video, or you want to control something else, you can do a gesture to swipe it. So to do just this one gesture, we had to design 300 cases of where the gesture can happen. Remember, it happens in different locations, different places. We have almost 8,000 participants, 71 days of data collection. We had people to have to go and collect the data of the gestures in front of the phone. It was not feasible, so we built a robot to do this gesture collection instead of the people, and it just took exceedingly, like only Google can do this kind of projects, right? It's just like it's nobody else can do this kind of stuff. And then what happens when it was quite, people were happy about it. When we did it for the Nest, we have to repeat the same process for the new product, because you couldn't take design from the first model the first one from the Pixel, and move it at Nest, just the same gesture, because you changed location of the sensor, location of things, use case is different, type of gesture slightly different, doesn't scale. So this is a problem. So you can't, it's easy to build AI models for digital world, because your data is available everywhere, and it's always the same, doesn't matter where you are, the same data. In the physical world, building this model is extremely hard. So to solve that problem, we started Archetype. 5 of us left Google about a year and a half ago, and we decided to focus on a new direction in AI, which we believe is going to be the major directions in AI going forward, which we call physical AI. In the physical AI, we think about it as a new form of artificial intelligence, which is not just looking at things online, not looking at the things people already have access to. It's not a chatbot, but a physical AI model, which is a single foundation model, which can perceive, discover, and reason about the hidden patterns in the world around us and behaviors in the physical world that otherwise escape human perception. So AI can do better than us. AI can help us to be better than us. And when we started, we were kind of the first to start pushing this vision of physical AI, recently becoming quite popular. Jason Huang, NVIDIA CEO, recently just came up and said, like, the physical AI is the next big thing. Now, he thinks about robots. Our differentiating difference is that we're thinking about building a horizontal model which can take care of a variety of use cases and a variety of applications. We think about as a model which can encode the entire world and be helpful for everybody. And we call it the model called Newton. And it's a horizontal foundation model which can learn about physical world from the data. We can teach the physical world about physical world. And then it can help us with our daily operations. So let me show how the Newton actually designed first. And then I will show some examples of our first version of Newton. We don't show it many people, so you're probably one of the first to see some of the examples. And some of the examples of applications we're working with the partners and clients, customers on applying Newton for physical world. So the way Newton works is that right now all the data is separate. It's actually quite a simple idea. You have one model separate. You have a data. For each one, you have a separate model, and each one you kind of tuning one-to-one. What we're proposing there is to map output from Newton in a single embedding space, a single representation where all the sensor data lives. And then from that representation, we can map it into a variety of representations. It could be pictures, it could be images, it could be anything else. Because at the core of it, Newton is a generative model. So it can generate any kind of representation from the captured applications. So what can you do with this? What kind of things you can do with this? Well, we're working with a few consumer electronic companies to make spaces which will even smarter than before. Right now, you have a bunch of sensors everywhere, and people don't want to have cameras in their world, but they want to have space, smart. They respond to them, understand what's happening. So how can we connect a variety of low-key sensors and then integrate them together to understand what people's intent are, what people want to do, without capturing the actual photographs? So this is an example of a Newton. On the left side, you can see what Newton sees. It's a radar staying at the table. In the middle, you can see the display showing what's Newton inside, like this embedding space. In the right, you can see how the Newton can describe the radar directly to the language. So let me show from the beginning. So I'm going to make another loop. So you have a single on the left, the person's coming in, a customer to the store, and the model can say, a person is approaching, a person is stationary, and very brief descriptions of what person is doing. Person is there, person is receding quickly, and nobody is there. So this is an example of the model being able to describe very complex radar data, as I showed you, very complex, into the simple language. Now, the radar is very simple. If you can use the camera, you can do so much more, obviously. So this is an example of using camera to describe. Newton describes how the person making tea, right? So you just got person pouring tea in teapot. So the model runs from the computer. It can see the person. You can see the video on the computer looking at the person outside of the world. And in real time, it goes to the cloud and be able to transcribe person activity in the physical world. And the use cases we have for that is actually quite common. It's safety, maintenance, measuring what people do, how people perform in the world. People don't do unsafe motions, creating work lists and so on and so forth, right? Because understand what people do in the physical environment, construction workers, and transcribe it in the set of actions they're doing. Now this is all about human understanding. We're also thinking quite a lot about the opportunity to use Newton for things like factory controls and be able to find anomalies and find issues with the data they have. What would be, something happens wrong, something goes wrong. How can Newton find those things? How can make it easy for people to understand? And this is an example of the video where the Newton uses multidimensional sensor, which is accelerometer, and you can see lines of accelerometer. And now you can see how we're using text prompt to tell with Newton what to do. Here we are asking Newton to track a transit status. And as the person moves around with the package, it says the package is still, and package is in motion, and kind of looking at position of the packaging. So, and you control it purely by asking questions. So you can ask the questions, can you tell me package mishandling? Can you look for anomalies in the data on the packages? And now with the same data, Newton is capable to understand what's the person, where is the person's package is shaken, is it handled gently, or is it dropped? So you can start looking for anomalies, and you program Newton by asking questions. You don't pre-program Newton through dashboards or applications. You can ask questions in the regular language and ask almost any kind of question. And the use case people looking for, like we're working with logistic companies with shipping very expensive drugs, very expensive medicine like cancer drugs and vaccines, and they need to know what happens during the supply chain and completely track through the time of supply chain what happened with their package. So accelerometer is easy to put in, but data analysis is very hard. So this is one of the use cases we're talking about. We actually have it done on the drone too. So it runs completely can run completely on the edge, and the drone flying around is through 5G. It talks to the sense to the local cluster, and can describe what's happening when the drone sees. It's kind of hard to see, but on the top you can see the line, and there's the questions we ask. Is anyone on the bridge? And they say, no, 3 people on the bridge. So Newton in the real time from the drone can describe what's happened on the bridge. Or you can ask the questions, where are the most people on the bridge, or 3 people are currently on the bridge. And I think you can ask something, is anyone on the building rooftop? So it's going to keep asking those simple questions, and the Newton can describe directly from the data. You can ask, railway, is anyone on railway tracks, or there's no railway tracks, so on. So it's actually quite powerful. You can ask high-level questions to Newton about the physical world. Undefined, unprogrammed before. We didn't train the model for that. It's be able to answer these questions about the physical world, running on the edge. Now, interesting thing here is we also work with quite a few automotive companies. And automotive companies are interested in how to create. You cannot use text when you drive, right? You cannot use text messages, it's distraction. So how can we remember that Newton can output not just text, but because a generative model, it can output a variety of representations, such as visuals. This is an example of the video. We have a customer working with somebody in India where you ask him, can you track a car in front? And now instead of showing you image or text where the car in front, it's create this orange overlay heat map where the car in front. Now, car is obviously not a car, but when you're driving around, you can see the car in front. And now you can ask. So now you can ask pedestrians, now I don't want any more cars, I want to track for pedestrians. Tell me if there's any pedestrians around. And now as you can drive around on the right side, you can see all the red heat maps are trying to understand where the customers are in the space. Again, doing quite good work on that. And now what you can do, you can combine them together, and you can ask very general questions, such as, show me crowded areas. And now what it does is combines very high-level questions. It combines all those things together and draw your little heat map on the map, showing the crowd areas. And the use case here is that you have delivery fleets, you have delivery cars, the taxi services, and they drive around, and you want to avoid crowded areas. You want to avoid different obstacles, so you can plan your route efficiently. One of our investors is Amazon, and that's something which people are quite interested in. So I think this is some of the examples, and I can go for a long time, but I would like to kind of start to conclude things, is that there's a big difference between generative AI today and what we're trying to build with physical AI. It's quite different. In generative AI, you talk to AI, and AI is sort of in this box, in this vacuum, and it's not connected to the physical world at all. It's a kind of compendium of knowledge, just like talking to an encyclopedia. In our case, we look at AI as something which is connected to the physical world, and AI is your interface, is your lens to look at the physical world around. So this is sort of like a big so you look through the world, and AI is augmenting your physical world understanding, which is captured through sensor data. So we come up with this concept. It's like everybody's talking about agents now, right? The agents are the next thing, there are going to be agents there, and then so forth. I don't like the idea of agents. I think agents suggest some sort of anthropomorphic qualities and some sort of individual thing. We're thinking about AI, as I mentioned, as a lens, as a new kind of lens. You're looking at the physical world. And it's sort of semantic lens where you can focus it on things you're interested in by using language. You can turn it and say, show me traffic, show me transit status, and the lens showing transit status. And you can say, okay, well, now I want to see package mishandling as a previous example, and now show package mishandling. So this is how we think about AI. That's how we believe AI is going to be, as a new lens which augments our perception of the physical world with information and knowledge we don't have. So it's not an asteroid which is going to hit the Earth, and it's not an alien, the way we see this. Just like Isaac Newton used lens to discover the structure of the universe and the structure of the light and the physical world, we believe that AI is going to be the very powerful tool which is going to help you to discover the physical world in the way you wanted to discover. So thank you.